Hello, everybody. Welcome. It's great to see you all here. If you're in this room or if you're tuning into this talk, it's likely that you're interested in understanding what's happening at the cutting edge of technology, emerging technologies. And in particular, maybe judging by the title, you might even be interested in the emerging quantum technologies and understanding what you can do with that or how it can impact your business, your customers, help solve some use cases. Could be just that you're interested in learning what we're doing in quantum technologies at AWS or more generally and abroad. Or maybe you actually want to get into some of the details of implementing a real quantum network or some kind of quantum solution yourselves. You want to see what it is that goes into doing that. Now, we're planning to give you an answer to at least some or all of those today. But if none of that sounds right, you're probably in the wrong session. But don't feel obliged to stick around. For everybody else, and for those of you tuning in virtually and around the world wherever you happen to be, thanks for being here. My name is Grant Sultan. I'm joined by my colleague Cyrus Proctor, and also we're very happy to have Lee Sattler from Verizon Communications. We'll introduce them a little bit later. So with that, let's dive in. The plan for the session is to start with a very lightweight overview of what we're doing in quantum technology at AWS. Very lightweight, lightning speed. And then I'll tell you some of the differences and similarities between quantum networking and quantum computing, what we mean when we say those two terms, and what we're really trying to get after. After that, we'll do a little bit of an introduction to what, when people talk about how quantum computers can pose a threat to cybersecurity, what we really mean by that, and how we can actually counteract that with new and emerging quantum technologies, for which Cyrus is an expert. And with that said, I'll then hand it over to Cyrus to tell you about something called quantum key distribution and how that solves this problem of a threat to cybersecurity from quantum computers. Cyrus is also going to work through some of the details of a practical implementation of building a real quantum network for quantum key distribution, things we've learned in doing that, and then hand it over to Lee to walk us through some of the use cases and why that's important, where it's headed, as well as show you some of the details and results and key takeaways from this new thing that we built. Okay, so let's jump in. We'll start with just quantum technology at AWS. And I said lightning introduction, that's really because this has been covered in previous sessions this week. And if not, it's also been covered in previous reInvents, and those talks are often online, so I'd encourage you to go check out some of those links, or find me afterwards, or we'll put some links up on the screen afterwards, so be ready with those. Very roughly speaking, there are four main pillars of quantum technology at AWS, four main efforts. There are two that are not really in focus for this talk. They're not in scope. These last two here, the AWS Center for Quantum Computing and Amazon Bracket. But just to leave no stone unturned, I'll go through them quickly. The AWS Center for Quantum Computing is a new research institute within AWS and in collaboration with Caltech, the California Institute of Technology. They have a mandate to design and build a real quantum computer. So that's the hardware, the architecture, the classical control, also the theory side. There's research into error correction and algorithms and application design and things like that. So that they're really doing all that hard research and development work to bring them to fruition. Amazon Bracket is a cloud service alongside all the others that you're familiar with for on-demand access to quantum devices. There's a suite of QPUs, quantum processing units from third-party vendors right now, as well as a number of fully managed quantum simulators, which is a classical way of simulating the effects of a quantum computer. There's a nice SDK. There's a number of other features that let you, for example, run hybrid quantum classical workloads in the cloud. Yeah. Putting that aside, the other two that are in scope, there's another one called the AWS Center for Quantum Networking. And this, similar to the Center for Quantum Computing, this is a research group within AWS. Sometimes we'll say CQN, so if you hear us say that throughout the talk, that's what it means, the AWS Center for Quantum Networking. And instead of designing and building quantum computers, they're designing and building quantum networks, the technology required to implement a next-generation communications network using quantum mechanics. As part of this, they work closely with customers and external collaborators, for example, Verizon Communications, to develop these state-of-the-art proof of concepts, which we'll show you done a little bit. And they have a research and development lab in Boston, and they have an alliance with Harvard University. The fourth and final pillar is this Amazon Quantum Solutions Lab. And this is an interdisciplinary research group. It's part of AWS Professional Services. They work closely with customers and external collaborators to solve any sort of hard problem that a customer comes to us with. So you have a use case, you want to solve it, you're not sure how, you want to see how you could use a quantum computer, you want to see how you could use quantum networking, maybe you want to just have any sort of solution that comes to mind. That's what this team does. They're tool agnostic and solution oriented. They have a diverse background in things like quantum technology, as the name suggests, quantum information theory, quantum computing. But as well, there's experts in machine learning, high-performance computing, and classical optimizations research. And generally, we sort of try to focus on a hybrid method or any solution that's best suited for the problem. This Quantum Solutions Lab group is closely integrated with the rest of AWS professional services and also with these other teams. For example, the Centers for Quantum Computing and Networking. We work closely with them. And we spend a lot of time thinking about customer use cases across a bunch of industries, verticals, you name it. We've thought about how to solve various problems and how you might be able to do this with any sort of emerging technology. And so if the point here is just to advertise a little bit that if you have a problem that you'd like to solve, you're not sure how, or maybe you want to just find a new or different solution to it, you should get in touch. And there's some contact us information coming up a little bit later. All right, but let's get into the meat of things a little bit. So I've been talking about quantum computing and quantum networking. And these are two sort of different terms. They're both sort of subgroups within the umbrella term of quantum technologies. Quantum computing and quantum networking, they have a lot in common. They both make use of the laws of quantum physics and quantum mechanics to operate specialized hardware that run or that solve some sort of computational task or some sort of information processing task, I should say, using, for example, the building blocks like qubits. It doesn't have to be a qubit, but that's the most common sort of core piece of hardware. They're specialized machines, and they're both subject to noise and errors and kind of the same difficulties that we've known that we hear about in quantum information theory. But where they differ is in terms of the task that they solve. So a quantum computer is more geared towards computing, as the name suggests, or solving some kind of some sort of computational problem. So you have a calculation you want to run, you formulate it in a way that's amenable to run on a quantum computer, and then you run some kind of quantum algorithm, for example, using a digital gate-based scheme on a fault-tolerant machine. The point here is that you're really processing information for the sake of computing. And by contrast, quantum networking is more geared towards information transmission, whether that's classical information or quantum information. Instead of computing something, you're really just trying to transmit information using the laws and the properties of quantum mechanics to do so maybe more efficiently, maybe more securely, many things you can do. And quantum networking naturally lends itself to a number of standalone applications. For example, quantum key distribution, which is going to be in focus today. But you might think about, if I had two quantum computers in different parts of the country or different parts of the world or something, and I want to connect them so that I can have them run together some larger computation, I'd need to be able to connect them in a way that lets the quantum information transmit between them. And that's one application of a quantum network. Another one could be just sending classical information, but in a way that's provably secure against attack using the laws of quantum physics, and that's going to be in scope today. Good, so let's drill down a little bit on this problem I mentioned earlier about how a quantum computer can pose a threat to cybersecurity. So many of the most commonly used cryptographic protocols, the way that we access our online banking or communicate through secured end-to-end text messages or something like this, they rely on public key encryption schemes like RSA or elliptic curve cryptography, which have an underlying assumption that it's really easy to encode information and very hard to decode that information or to crack the code unless you know some sort of secret key. So you have some sort of information that you want to keep secure, you encrypt it, and the assumption is that nobody is going to be able to break that code unless you tell them the key that you used to encrypt it. And that's an assumption that we don't know of a good way to break that code using. There are no algorithms that we know that can sort of jumble up that, unjumble that information. But it turns out that there are such algorithms that run on a quantum computer. So we have examples of algorithms that could efficiently unscramble the encoded information without knowing that secret key. And so an example of this would be Shor's algorithm, which can break the RSA factoring scheme. But what this means is that using future quantum computers, larger scale, cryptographically relevant, we should say, which means they're sufficiently large that they've got enough resources to be able to run these algorithms. Using those, we have algorithms which can crack these crypto systems. And that means that our information is vulnerable to a quantum attack. Now, to get around this, we can either upgrade, there are multiple ways, but we can upgrade our encryption scheme to something that is assumed to be hard to decode using both quantum and classical computers. That's called post-quantum cryptography, right? We have the way in which we take our information and encode it or encrypt it. We just do that in a way where we don't know how to break the code using even a quantum computer. But there's another way to do this, and that's what we're talking about today. That's called quantum key distribution. So if you are able to somehow distribute that secret key such that nobody can ever provably intercept it, and you encode the information in a way where it cannot be broken unless you have that key, you could somehow get around this problem. And crucially, this means that there's no underlying assumption about the hardness of cracking the code. Right? This is independent of that. So for example, you could use something like a one-time pad and then use quantum key distribution to transmit the key. Now, I said a second ago that this is important when we'll have future quantum computers that are cryptographically relevant, large, powerful, and can run these algorithms. And current state of the art is not close to that. We have a long way to go, and it's a difficult scientific and engineering challenge to get to that point. We have many hurdles to overcome. And so you might wonder, well, why do we think about this now? Is there any urgency? And do we need to worry about this right now, or should I just put this off until somebody announces a nice fault-tolerant computer? And it turns out that the answer is a little bit nuanced, right? If you have some information that you want to encode or encrypt and keep it secure for a long period of time, that amount of time depends a little bit on the sensitivity of the information. Because an adversary could just take that information, if you're just transmitting it in an encrypted way, store it, and then wait for a quantum computer to come around and then decrypt it. And if it's important that information stays secure indefinitely, for example, then this is a problem. Somebody will be able to break it in the future. And so you might imagine that there's some timescales at play here. And in fact, there are three. The first one is this thing I was just sort of describing, the shelf lifetime. How long do we need the information to stay secure? How long do I have to worry about somebody being able to crack it? Yeah. The next one is called the migration time. And that's how long it will take you or whoever has the information to upgrade their system and their existing infrastructure to use one of these newer schemes that's resistant to a quantum attack, whether that's quantum key distribution, post-quantum cryptography, anything else. Right? There's some amount of time required. And these can be in parallel, they can be in series, but in the worst case, it could just be that there's a total amount of time required for your information to remain secure and has to be secure such that you're able to upgrade. And then now is the red one, the threat timeline. This is how long it'll take for us to have one of these large, cryptographically relevant quantum computers. And if that time is quite long, if it's going to take a very long time, then maybe we don't have to worry. But in some cases, this shelf lifetime, that could be decades. And indeed, some government agencies have mandated that their shelf lifetime is several decades. It depends on the sensitivity of the information. Top secret information has to be really secure. Cat pictures, maybe not. So it depends a lot on the information. And indeed, if that time is quite long, and it turns out that we actually get one of these quantum computers in a shorter time frame, then there's a window here where that information that was encrypted is now vulnerable to attack by a quantum computer. And so now how do we get around this? One way is by using this thing that I mentioned of quantum key distribution. And so for that, I'm going to introduce my colleague, Cyrus Proctor. Cyrus is a research scientist in the AWS Center for Quantum Networking. He's also an expert in quantum key distribution. So I'll turn it over to him.
All right. Thank you very much, Grant. It's great to be here today. Glad to be with you. I'm excited to be able to talk about quantum key distribution and also the milestones that we've achieved with our colleagues at Verizon. But we'll get to that in a little bit. We still have a little bit more that I want to talk about before we get to the actual achievement. So, Grant has introduced us now to the concept of a cryptographically relevant quantum computer, as well as this scenario of store now, decrypt later. If any of you have already seen Peter DeSantis' Monday night keynote, at the end, he actually does talk a bit more about this type of scenario in the Center for Quantum Computing section at the end of his talk. So you may want to go back and check that. That's already up on YouTube. So, quantum key distribution itself. Briefly, when we think about this, what we want to think about is how are we transmitting information confidentially? In general, we have a party who's at a secure site. Her name is Alice. She has some sort of key that she has created, and she would like to talk to a remote party, her colleague, Bob. And there are schemes already out there today that do this, right? We have public key cryptography that we're doing key exchanges. Quantum key distribution is another way of doing a key establishment between two remote parties. You can also think of doing some sort of key establishment where if I wrote down a secret and I gave it to you in person, you could take that and then we both have the same shared symmetric secret that we can then use to encrypt and decrypt information. Now, obviously, that's a bit impractical at the size and scale of the internet. So when we're talking about this, we want something that eventually, if it's going to work, it has to be able to scale up. So quantum key distribution, in general, what we want is we want to create this key. In order to do that, we have to use an established protocol. These protocols have been around a long time already, in fact, many decades. And Alice is going to carefully prepare the keying information in the form of quantum bits. These quantum bits are actually photons, specialized photons in this case, and she is going to send them over to her friend Bob. Now, when she does that, she is hoping that most of them are going to make the journey over, but just like regular photons and regular light, sometimes we're going to have absorptions, sometimes we're going to lose some of our content. We have losses along the way here, and so not everything gets to Bob, but that's okay. Now, we have our photons going across, our quantum bits. We're sending these as single photons. We're not doing this as a laser, for instance. It's individual photons for this quantum key distribution, at least in the typical sense, okay? There are multiple different flavors of quantum key distribution. I'm just describing a basic one right now. So Bob is receiving these photons. He is taking them and he is doing a measurement of them. He is using a single photon detector or multiple single photon detectors as these bits come in. And Alice and Bob are then talking back and forth to each other using this protocol that I mentioned earlier in order to decide how to distill down and choose their secret key. They're not distributing information about the key itself. It's only metadata that they talk back and forth on a classical channel to each other. And once they do this distillation step, they end up with a symmetric key that they can then trust and use for encryption and decryption, much like we would use today for AES. Now, if they do this, that looks a lot like our public key cryptography schemes today. In fact, the way that this works, we can combine the keying material that's coming from QKD with the other encryption schemes or key establishment methods that are out there, and we can use the symmetric keys together in what's called a hybrid implementation. So that not only would I get, say, the benefit of the public key cryptography schemes that we have, but I could also benefit from quantum key distribution. In other words, both of them would have to be vulnerable in order for my confidential information to be also vulnerable. Now, in general, back to store now, decrypt later. How does this help us? Well, if we are able to do this in a way that doesn't require an algorithm, like say RSA or elliptic curve Diffie-Hellman, if we're not doing that integer factorization step that is vulnerable to that quantum computer, then we don't have to worry about outpacing whatever the most powerful system is going to be. And in this case, this is about it. It really is as simple as sending individual photons, encoding the information in a way that you can then use the protocol to agree upon your key. And you don't have to worry about what's coming in the future. What's more interesting, though, about this quantum key distribution is also the fact that we are using these quantum bits. Now, in the ideal scenario, we don't have an eavesdropper. We don't have noise on our channel. We can send these photons, and they're going to arrive over at Bob's site. In the event that there is an eavesdropper, though, let's say that there's somebody in the middle who is trying to listen in on the conversation. They want to do the store now and then hopefully decrypt later. right? They have that powerful quantum computer. Well, in this case, we can give the eavesdropper all of the computational power that they want. They have the biggest quantum computer they can imagine, the biggest supercomputer that you can imagine. It doesn't matter, because in this case, when Alice is transferring these quantum bits over, if the eavesdropper is doing a measurement, they have incomplete information at this stage. And there's one thing about quantum information, is that if you are doing a measurement with an arbitrary measurement on a state and you don't have complete information, you cannot copy it. This is known as the quantum no-cloning theorem, and it actually is something that is like an underlying pillar for this quantum information. It means now that the eavesdropper has done a measurement, they have information from Alice, and they're going to try to continue to forward it along to Bob. Now, if they try to do that, Bob is going to receive that, and Alice and Bob have a way through their protocol to determine that this has been tampered with. There is no analog that we have today in classical communications. This is something that we get for quantum key distribution. As a result, they end up not trusting that material that's either been tampered with or has been observed. And that's pretty cool. So at the end of the day, QKD is providing a provably secure, shared, random, secret key. And we would like to be able to use this to encrypt the data and messages that go back and forth between Alice and Bob, and maybe their friends. So let's talk a little bit more about practical implementation and what these QKD systems actually look like. Surprise, they've been around a long time. This stuff is not new. In fact, the protocols, like I said, they've been around since the 80s, the 90s. The actual commercial off-the-shelf systems, they've been around roughly 20 years. And there are more and more companies today that are starting to actually pick up the technology. And they're becoming quite robust. At this stage, these devices are typically rack mountable. They go in a data center. They're not that big. They're 1 to 3 rack units, which is roughly about this big. And then, think of like a pizza box. Now, Alice and Bob, they come in pairs, right? You have one at Alice's site, you have one at Bob's site. And you're going to connect them up somehow. Now, we can do this with fiber optic cables. What's really interesting about this is that the fiber optic cables that would be used can be standard telecom fiber. We don't need anything special here. The same thing that we're using for our internet backbone today, we can use for this quantum key distribution. Now, those quantum bits that we're sending, those are sensitive, right? Any sort of touching or measurement of them, and they are going to collapse. So we want to typically have a dedicated fiber for that, and we call that our quantum channel. It doesn't have to be. In certain cases, we can multiplex our quantum bits with classical information. You have to be careful about it, but it is certainly possible, and you just have to decide about what kind of performance you're looking for, and what are your design requirements in terms of your network. The other thing that we need is we need a way to communicate classically back and forth with each other. So this is our classical channel. So this is a public channel. It needs to be authenticated, but this is essentially how Alice and Bob are doing the key distillation and saying, okay, I received this bit, now what? And the other thing to note here is that this is a point-to-point technology. Right? We have Alice and Bob. I haven't extended this yet. So inherently, we need to make sure that we can get our photons from one site to the other. We cannot amplify this signal. That is another part of this no-cloning theorem, right? So I can't copy this information without destroying it. This means that we are limited in the distance that we can send these quantum bits, these photons right now. And typically, for commercial off-the-shelf systems, that's under 150 kilometers at this point. Now, I imagine that things will probably continue to do better. There are some labs that are doing great work in this area, but we are fundamentally limited here by the properties of the fiber itself and essentially how many photons we can generate. So for now, if we want to do an extension, we are using something called a trusted node configuration, where essentially, instead of having 2 units, we now start chaining these device pairs together to create a network where we can distribute our quantum keys from site to site to site. Now, if I did extend that network, one of the things that's a caveat today is that we do not have vendor interoperability yet. There is work in this area, but it is early days. So that means if I buy a QKD system from vendor X and another one from vendor Y, and I would like to chain them together, I may not have the capability of doing that. There are some limited cases where that might be possible. We're going to have to overcome that hurdle. The other thing about this is, in order to actually scale up here, we're going to need to deal with key management. These are symmetric keys. These are not like the keys that we typically think about in public key cryptography. So in that case, we're going to have to figure out what that key management looks like as we start to scale up that network. Now, I've been talking mainly about key creation from these devices. The other side of that is the ingestion or the consumption of these keys, right? So we create the encryption keys. We use something like AES, perhaps, or maybe one-time pad, as Grant mentioned. And we then consume those for encryption and decryption. There are hardware devices that exist, and we use them all the time in our classical networks. Verizon, I'm sure, has plenty. AWS has plenty. They're known as link encryptors, and they work all over the network stack, right? We could be at layer 3 with VPNs and IPsec. We could be at layer 2 with MACsec. We could be at layer 1 with optical transport networks. It just depends. And QKD keys are applicable in any of these scenarios. In fact, you could go up further the stack into TLS if you were so interested. At this point, though, we're working on specifically how do we get the link encryptors to ingest these keys that are coming from this QKD device. And it turns out that a lot of the commercial manufacturers have already written software modules to do this. It's not terribly hard for them to ingest out-of-band keys in a way that makes this work, and they can provide a secure tunnel between their sites. So, with that, what exactly is it that we did? In this case, Verizon, or my colleagues at Verizon and the Center for Quantum Networking, we have put together a multi-site, multi-vendor quantum network. It's a rudimentary network. It's a QKD network. There are many applications that we could build up on this, but this is a layered approach, and this is a starting point. So the way that we have approached this, we start from the bottom and we work our way up. At first, we're talking about a physical layer. The physical layer is going to actually be the secure sites where we house the equipment. And then we need fiber optic cables that are going to be in between these sites. And in this case, the sites are owned by AWS and Verizon, and they're also at a co-location facility. I'll get more into that later. The next layer up is the distribution layer. The distribution layer is actually where we have these QKD paired devices. And essentially, we are setting them up at each of the sites, and they are doing their quantum key distribution in a point-to-point configuration. From there, we have a key management layer. That key management layer is taking the QKD keys from below, and it is making them available for use in encryption and decryption from consumers. After the management layer, we have the consumption layer. This is where the use cases are. This is where we use, say, our VPNs or maybe our MACsec type link encryptors, and they are consuming our keys. So let's dive in a little bit more. Looking at the physical layer itself, what is it that we have put together? Well, these are 4 different sites up in the Boston, Massachusetts area, and we have at least one of the sites 55 kilometers apart. Now, there are 5 site-to-site fiber connections that are in between these different sites. And what does that mean? It means that we don't have a full mesh topology. Now, we do have redundancy here. There are multiple routes from one site to another. In the case of one of these links not being available, you can still route from one site to a different site. The other thing I'll point out here is that we have two sites that are at least not directly connected. In fact, they are 2 hops away. On the diagram here, that's VZ1, and that's the co-location facility. So the other piece that's important about this, these sites that we're using, data centers, labs, offices. Why does that matter? Well, these quantum key distribution devices are commercial off the shelf. Part of what we're here for is to test them out, see what they're capable of. Are they really production ready? And in this case, we're subjecting them to varying temperatures, humidities, dust levels, vibrations. All of these are going to matter because at scale, we need to understand what the failure modes look like for these QKD systems. Moving up, now that we have our physical layer, the distribution layer itself, where we have the quantum key distribution devices all spread out, these are coming from different manufacturers. We have 4 different models from various manufacturers that are being used throughout this system. They're all in point-to-point configuration by themselves, and it's a partially connected mesh, right? So those 2 sites are at least 2 hops away. And on top of that, the QKD keys right now are staying rack local. In other words, when they are created from being measured as those quantum bits, they're staying right there at the rack that they're located at, and then next to the management layer. The management layer itself sits on AWS edge compute devices, specifically Outpost servers. And these devices are a compute platform that we use essentially to write software. And this software is pulling the keys up from the QKD devices. And then in our case, when we have a non-direct link, it's making sure to essentially forward along keying material. And we're using this one-time pad encryption to do so. It's distributing the keys in such a way that it's effectively a fully distributed network. You don't see the difference. So any user at any one of these nodes can ask to talk to their neighbor or their friend, and there's going to be a key available to them. There is no single point of failure in this case. Depends on how you architect your network, obviously. But in this particular example, if we took one of these links down, it's not going to be a problem because essentially we can reroute and still use other links in order to maintain our encryption key supply. And in this instance, this is a trusted node-based QKD network. It's heterogeneous with these links because we have all of these different vendors and their QKD devices. Lastly, our consumption layer. The consumption layer in this case is a set of IPsec VPN hardware encryptors. They're housed at each one of the sites, and we are creating VPN tunnels in between as needed, and they are consuming the QKD keys that are coming from the management network. Now, these VPN tunnels are happening over the internet. They're also direct fiber. It doesn't really matter. But what we can do is we can combine these QKD keys with classically generated keys as well. So this is your elliptic curve Diffie-Hellman keys. And what that means is we're using a hybrid scheme. So we have both of them. And we have it set up right now where if we were to lose the QKD key generation, then our VPN tunnels would fail closed. In other words, they would turn off. This is just a configuration setting, and it kind of depends on how you want to architect your network. But essentially, because of this hybridization, you could choose instead to just go back to a classical algorithm or perhaps to a post-quantum cryptography algorithm in the future. Now, with all of this being said, we put this together. We've implemented this QKD network up in Boston. We've designed it. We've made sure that we got the fibers together. We built it out. We've tested it, configured it. We're collecting data right now. We are essentially getting all of the telemetry, and we're learning from it. But in order to know more about the why and the how, I would like to introduce my colleague, Mr. Lee Sattler from Verizon Communications. Welcome, Lee.
Thanks, Cyrus. Okay, so let's talk about why this is important. Let's start with this. I mean, Cyrus just talked to us and said, hey, you have these two QKD devices. They're point-to-point. But I can't actually connect a QKD device from vendor A to vendor B, right? Because they both have their own way of implementing QKD, perhaps using different protocols, different optimizations. But if we're going to build out a large QKD network, we really don't want to use just one vendor because there'll be different performance characterizations from each vendor that might be optimal in different situations. For example, one vendor might be able to produce a very high rate of encryption keys. Another vendor might be very good at going long distances. Another vendor might just be average, and that's okay. Maybe that's what we need in that situation. And so by building out what we've done and taking that interoperability away from the QKD devices and putting it at a management layer, we now can start to use different vendors and build out an optimum network. The other thing with QKD is, as Cyrus said, it's been around for a while. I remember the first QKD device I got in my lab in 2019. It was like 6 rack units high. And it was a lot of work to keep it running. But in the short term, in the last 4 years, we've seen a lot of improvement in these QKD devices. Cyrus said now they're 1 to 3 rack units. They're able to go further distances than they were 4 years ago. They're able to generate more keys than they were able to generate. And so we've been keeping an eye on that and continually testing the technology as it improves. And then, of course, the idea is, well, what if I do want to put this into production? And this concept of production ready or operationally ready. If I put this device in production, I just want it to be out there, configure it, and have it just run. I don't want to have to worry about, is it running or isn't it running? It should just run. In fact, we like it to run with the 5 nines. That is 99.999% of the time, this service should be available. One way to get to that point is to consider the ISO model for FCAPS. That is an acronym for fault management, configuration management, accounting, performance, and security. These 5 elements are very important. Fault management, look, we want to know when the thing has gone down, and we want to know why. And if it doesn't tell us exactly why it's gone down, we at least want to have a hint from the messages that we get so we know where to start troubleshooting. Configuration management. We want to be able to configure the devices to operate in the most optimal manner. So there's going to be tweaks that we want to make to the configuration to fit the environment that we've deployed it in. Accounting and performance, well, those are standard things that we need to know. We need to receive that information so that we understand how well the system is working. And of course, security. Security has to be built in. That is a very hard requirement, right? And look, this QKD technology really is the first quantum communication technology that we can buy off the shelf, put into our networks, and actually start to experiment with quantum communications in a telco network. There's a lot of things that we don't know until we do that, because working in a lab, everything's pristine, and it's going to work fine. But when you get into the variables that are out in production, you might see things very different. And it's important to find these things out now. It could be a lot of different things that might affect quantum communications. Maybe the weather, sunny, rainy, cloudy, temperature, traffic that's running over buried fiber, things that are in the central office as part of the fiber infrastructure, the connectors that we use, the types of patch cables that we use in the central offices. All these things you're going to want to know ahead of time so that when it comes time to build a quantum communication network, you can plan for it and build it right. And of course, if you're going to run a network, you need to know, especially a quantum network, because it has all these new, it's a very different type of communication. As Cyrus mentioned, it's qubits. The information is encoded on single photons. So there's new things that we have to measure and understand in order to know how the network's working. Things like qubit errors, dark counts. What's going to be really important to ensure that we can properly manage and operate the network? So we've thought about this for the trial that we've done. And we said, well, we have our 3 layers. And across the top of this chart, we see key production, key management, key consumption. These correspond to the top 3 layers that Cyrus described. And then across the side, we have availability, rates, and status. And these are the things that we wanted to measure, right? We wanted to know, are keys available at each of these layers? What is the rate of production of keys? What is the rate of consumption of keys? What is the status at each of these layers? We can take that along with system telemetry data, common things that are available now, device error rates, system metrics. We take all that and we can combine it together, and now we have something that we can use to do troubleshooting and monitoring in our network. So one of the things, the availability that, or I should say the interoperability that I mentioned earlier is really important. But another really good benefit that we've gotten out of this is by taking and extracting the key management into a separate layer, now we can actually create bigger buffers for the keys, which are going to increase the availability of these keys for devices in the key consumption layer. And so what we're going to do next is show you a little experiment that we ran where we take down a QKD link. And so now these 2 QKD devices are no longer producing keys. Now, they do have a buffer, because the way this works is as the QKD devices are creating keys, they're storing them in the buffer. There may be devices that come and request the keys, and they come out of the buffer. As the buffer gets to 100%, then of course you have a FIFO, where the first keys that came in will drop out and the new keys will come in. As long as your key generation rate is higher than your key consumption rate, you should have 100% of your buffer full within that device. So this is a time series diagram. Across the bottom is the time, and it's on a 24-hour time period. Along the side of the diagram is the percent of the buffer that is filled. And we collected this data for all of our QKD devices that are in this network. And at some point, we went and took the QKD link down. And you can see where this starts to occur, where these blue lines start to dip down towards 0. What's going on there is, at the distribution layer, the nodes are requesting keys. There's no more keys being generated, and the QKD device is just feeding the keys out of its buffer, which is not being filled again. When this reached 0, we went ahead and turned the link back up. And so these keys, the key buffer once again started to fill. So how does this cascade up to the upper layers? All right, so here at the distribution layer, we now have our nodes. These nodes are extracting keys from the production layer, from the QKD devices themselves. Again, we have a time series chart, so time across the bottom. On the horizontal or on the vertical axis, we're showing the number of memory partitions that are holding our keys. And in each case, we have 1,000 partitions for every single one of our QKD links. Within those 1,000 partitions, each partition can hold 16 256-bit keys. And so you can start to see where once we took the QKD link down, we see this drop that's coming out of the buffer of our nodes. And that's because they can no longer get the keys from the QKD device. So we're starting to expend the buffers in our nodes at the key management layer. All right, but here's the thing. The scale on the side of this diagram, and I kind of tricked you a little bit, at the top of the y-axis, the value is 1,000. And at the bottom of the y-axis, at the intersect with the x-axis, the value is 950. So we didn't actually go down to 0 in this case. We only used 50 of our memory partitions. That means we still have 95% of the key buffer remaining. And just to let you know how these keys are being used up, we have a script that's running along with our IPsec tunnels, and we're making key requests at about 300 requests per minute. Once we turn the QKD link back up, in this case, we can also see that the buffer again begins to fill. At the rate that we were requesting keys and the rate that the buffer is being depleted, we actually could go about 30 hours with that QKD link being down on the bottom before the IPsec tunnels would go down. And then if we look at what happened at the consumption layer. So here we have same time series graph, except this time on the y-axis, we're counting the number of IPsec tunnels that are active. As Cyrus mentioned, if these devices that are requesting keys for the IPsec tunnels were not able to get a QKD key, it would take the IPsec tunnel down. And obviously it did not go down because it was still able to retrieve the keys from the distribution layer. So in this case, what we've been able to do is improve the availability of our system by building this key management layer with bigger buffers than what were available in the QKD devices themselves at the production layer. So what could come next? Well, obviously, if you build one metro area, it makes sense that you're going to connect it to another. Before I talk about that, I do want to mention this. In this diagram, I show a full mesh. And of course, it doesn't have to be a full mesh. But something to keep in mind, currently, QKD devices have a single interface. And that means that if I have one QKD link, I have 2 QKD devices for every link. Here I show 6 links. That means I have to have 12 QKD devices. That may not be a desirable situation, and I expect that is going to change. We've seen work already where people are creating spoken hub networks, putting an Alice node right in the middle with multiple interfaces and going out to the Bobs on the hubs. But now let's think about what if we're going to build this long-haul network. Let's say that our Metropolitan A is actually in Las Vegas here. And our Metropolitan A B is over in Los Angeles. The distance between the two is about 440 kilometers. Cyrus said that 150 kilometers is about the practical limit. So we can't use just one QKD or a pair of QKD devices. We have to do something like Cyrus mentioned earlier, trusted nodes. Now, the thing about trusted nodes, think about them like this. Think of them as 2 QKD devices stacked on top of each other. One QKD device is pointing back to the Metropolitan A. And then there's another QKD device pointing to the next trusted node. There's an Ethernet cable between the two. And the keys are being created in the first device and then being transmitted over that Ethernet cable to the second device. Well, now we're no longer in the quantum realm on that Ethernet cable. We're now back to classical communications. And you could say that that is going to be a security vulnerability because somebody theoretically could come to that Ethernet cable and extract the keys off of it. But there is a solution to this. You simply put that trusted node in a very highly secure area where people can't just walk in and get the keys. This type of topology has actually been used over in China to create a 2,000-kilometer network spanning over several metropolitan areas. Another option is to use satellite QKD. Well, it turns out that quantum communications can go much further using free space optics than it can over fiber. This topology has also been demonstrated, and again by China. They were actually able to go between two metropolitan areas spaced 2,400 kilometers apart. But there's a third option also, but it's not available yet. It's still in the labs, and it's called a quantum repeater. And in this case, all the communication is quantum. The qubits come into that quantum repeater, go into quantum memory, and then go back out. And so there's no security vulnerability there. This particular solution, quantum repeaters, will play a big role in quantum communications in the future. All right, so what are our key takeaways? Look, QKD networks are becoming a reality. These QKD devices are now commercially available off the shelf, and there's multiple vendors that are producing them. Going up the stack to the consumption layer, we have layered encryption products that are capable of ingesting QKD keys. We've tested layer 2 encryptors, we've tested IPsec, we've tested MACsec. And this implementation is suitable. It works on existing fiber, as long as it's good fiber. And it can be deployed within a data center infrastructure. And I also say there's a lot of standardization going on, both for quantum communications and for QKD. And we actually used two of the standards that are available in our trial. We used SE-QKD014, which is a way to extract the keys from the QKD devices and a way for the encryption devices to obtain those keys and deliver it to them. The other standard that we use is IETF RFC 8784, which is a way to take encryption keys into IPsec and use them. And so where do we see this going? QKD technology is continuing to improve. What we're going to see in the future will be more and more miniaturization. Perhaps one day the QKD won't actually be a physical box, but a module that could be plugged into a chassis. And maybe that chassis could have both Alice and Bob modules. We're going to see performance improve. We continue to see longer distances. We continue to see higher key rates. I talked about this operationally ready. We're starting to see the products implementing these network best practices. And we see this development that's going forward towards what we call a quantum internet. And one of the keys of that, as I mentioned, was going to be the quantum repeaters. We've also seen a lot of satellite QKD networks being discussed. Canada's getting ready to build one. The EU is going to build one. China's going to expand the satellite QKD network that they have. And we're starting to see larger deployments of QKD networks, mostly in the EU and Asia. And the EU is a great example. They have what they call the Euro QCI, which is the QCI being for quantum communications infrastructure. And they've started out just by building individual QKD networks in the European countries. And the next step is going to be joining these individual networks together. And this is going to become the basis for the quantum internet in Europe. So I would say the future for quantum communications and QKD looks very bright. And I would expect that in the next several years, we're going to see some very exciting things. And with that, I'm going to hand it back to Grant, who will have some closing remarks, and hopefully we can open it up to Q&A. Over to you, Grant.
Thanks, Lee. Yeah, we've definitely covered a lot of material today, a lot of exciting things, and I can say without a doubt that it's been a fun and exciting collaboration working closely with our friends at Verizon, and so you can expect to see some more coming out of this collaboration. We're just sort of getting started, so stay tuned for that. And with that, I'd like to invite you to join us as well, right? So break out your phones and follow one of these links. You can learn more about what we're doing broadly in quantum technologies at AWS, or get in touch with this Quantum Solutions Lab. That's a good point, first point of contact to get started. You can learn more about what the CQN is doing by following the last link to their blog channel. Or you can just email us if you've got questions or want to get in touch. And now that you all have your phones out, please remember to fill out the survey. We really do value this feedback, and it helps make reInvent better for next year.